And here we are once again. It's the physics video lecture. Psci 168, video lecture 31. We're working on solar energy, and for the next couple lectures we'll do some topics on solar energy, and I'll give a little overview what we've done and what we're going to do. So solar energy, what we discovered was the solar constant. That told us how much energy is available, and it's an intensity, which means it is power per area. So we have this 1,340 watts per meter squared. Maybe I should just write that denominator once more. So 1,340 watts per square meter. And if we want a practical number for down here on Earth, we can just use 1,000. Now this actually, since that's power per area, if you want to find out about the energy available, you may have to average over the day, okay? Because it's not 24 hours, of course. It's when the sun is shining its brightest. And I'll go into that later, how we can make those estimates as well to take into account that the sun's not shining all day and all night. But since we know that, we'll just keep that in mind. These are maximum type of values you get at noon. And good. So that was what we began with. We discovered the solar constant. In fact, we used our knowledge of thermal physics to figure that out. But this is energy per time, right? Power. And it can be converted into different forms. And that's what we're going to go into. So what we did last time, we talked about a solar thermal power plant, and I asked you guys to get a bunch of good images. I hope you find good things. And you know, when you're hunting for images, you can discover all manner of interesting stuff. So that's why I always want to send you out to get good pictures for your notebook, because you're going to discover stuff on the way. So solar thermal power plants, there are different types. And like I said, I was taking thermal physics into account. And in fact, we couple the reflected rays, make something really hot, and couple it to a heat engine. So what else is there? Something we've already talked about, but I'm just going to mention it. Hydropower is ultimately solar energy because it's based on the water cycle, okay? Because of the water cycle. So we've talked about that before. I'm just going to bring it up. Another form is going to be the direct conversion of solar energy to electricity. We will do more discussion of that. I'm just listing it here. Direct conversion to electricity. But of course, at this point, we know that watts just refers to power regardless of whether it's mechanical or electrical or what have you. So direct conversion to electricity, that's going to be called the photovoltaic cell. Those are the things that people are putting on their rooftops pretty frequently nowadays. Okay, so photovoltaic cells. Another one, and this is what I'm going to talk about today, is wind energy. So wind, we know that's convection. And convection is due to uneven heating, which means there is heating going on. So that's why I'm including the wind energy in the whole solar energy chapter, because it's so broad. So we'll do wind energy today, bring a little physics into that, and not too long. I want you guys to go out and then get certain images of things and look a few things up for your notebook. So wind, because convection, because uneven heating of the atmosphere. It's hotter at one place, cooler at another, that's enough for there to be a breeze. Good, so that's what we're going to do now. Because I want to answer a question that's similar to this one. How much was there available in the sunlight? What we're going to find out now is how much energy is there available in the wind, in moving air. So that's our question for the day. So we'll call this wind energy. How much is available? You know, and we're discussing this regardless of how large, how massive the resource is. We just are going to apply our physics knowledge and get a good estimate for it. And then we'll see, it'll be similar to solar in the fact that it has its really good uses, and then it has some uses that aren't as impressive. Good, so how much is available? And first of all, let's list this again. We're talking about convection. We have a breeze. So that's a moving mass of air that's moving with speed v. A mass of air, moving with speed v. And this is going to go beyond air, because the formula that I get for this will actually be a good approximation for water as well, and we'll see the difference between air and water. So we've got convection, we've got a moving mass of air, and what kind of energy is related there? A moving mass, we say, has kinetic energy. Okay, so we have kinetic energy. And we remember our expression for it, 1/2 mv squared. But now we have to look a little more closely. Imagine that we have a box, and this is a box or a tunnel through which the wind is blowing. How about we have some blue arrows for our wind passing through this box here. And the box has a length down here of delta x. Okay. So we're going to ask about the mass that passes through this front edge here. Right, there's an area A. So we're going to ask about the mass that passes through there. So we have, I need a little more room to construct this. Yeah, so the mass of air is passing through that tunnel there, and we can estimate how much is in there. I just drew a cube. Let's go ahead and erase this here. Actually, it doesn't have to be a cube. It has an area and it has a width delta x. So we'll leave it at that. Let's go ahead and erase this. So here we go. Kinetic energy equals 1/2. Now that mass is going to be density times volume. Where have we seen that before? When we were talking about water, this time we're talking about air times v squared. Okay, so let's even label this just to make sure we remember. Density volume. That's why I said it could be air, it could be water. Right now we're thinking about air. Okay. So we have 1/2 density, all right, air. Now that volume is a cross-sectional area A times a delta x. Okay, so that's my volume, A times delta x, volume of that box up there, and I still have the V squared. So that's kinetic energy. We're almost done. Watch this. Now, with delta x is equal to V times delta t. What I'm saying is the air traverses the width of that box in a time delta t. Okay. Air traverses the width of the box in a time delta t. Distance is rate times time. And of course that's equivalent to, or V is equal to delta x divided by delta t. That's how we've learned about speeds, velocity, distance over time. So now we're all ready. We're ready to do this. So power is equal to energy per time. So what we're going to do is divide this expression by the delta t is equal to 1/2 rho A delta x times V squared, and we're dividing it by the delta t. That's where I'm bringing in that division. Power is energy over delta t. And this is a V. So suddenly we have equals V. So instead of V squared, we're now going to have a V times V squared, which is V cubed. And finally, I should be numbering this. Yeah, I am numbering it, right? 1, 2, 3, 4. Finally, I'm going to define intensity again, that we did before, as power per area. So 5 intensity equals power per area equals, well, I already have my power here, I'm just going to divide by the area. Okay, so it cancels the area there, and I'm left with, I'll go ahead and write it out here, intensity I equals 1/2 density, so like I said, divide by A. This is V, and this is V squared, V cubed. Okay. How amazing is that? That's a pretty simple formula for wind energy. We can say that's the wind energy formula, and the result is going to be power per area, which is to say watts per square meter. So watts per square meter of surface that's being that's subject to the wind. Okay, so you see all the physics we've done this semester allowed us just to pull this out here, very principled and good derivation. So you got 1/2 rho V cubed, and if this rho were the density of air, that would be wind intensity. If this were the water, say, flowing through a tunnel, okay, then it would be quite a bit larger. So actually, I'll bring that up in a moment. Because the question is, how dense is the air? Okay, so we need to know that. Okay, so that's our derivation for the wind energy formula. Now that we have it, let's go ahead and write it down and write down everything that we need to know about it. power per area of a fluid flow. That's really what this is. Power per area of fluid flow. I, it's an intensity is equal to 1/2 density V cubed. We will say, I'm just going to write here the units are watts per square meter. And let's talk about air for starters. So we need the density of air. So we use the Greek letter rho. So air, it's about 1.3 kilograms per cubic meter. Per meter cubed. You could look this up if you want something more accurate. Depends on the temperature, of course. 1.3 kilograms per cubic meter. So that's the density of air. It's kind of surprising. I don't feel as though there's 1.3 kilograms in this cubic meter of air, right? Because 1.3 kilograms is a chunk of metal. Or 1.3 liters of water. So that's actually a good point. Density of water is, of course, 1,000 kilograms per cubic meter. So yeah, air is just over 1,000, maybe 1/800 of the density of water, okay? But it still has some density. And so what we want to do is get an example of the power per area for a square meter of an airflow. So our example for V equals 10 meters per second. Now 10 meters per second, if you're thinking miles per hour, that's somewhere around 20 or 25 miles per hour. So that's a decent, strong wind, right? A decent wind. So, but you'll notice there is this speed dependence on the intensity. But so my example, 10 meters per second squared, I is equal to 1/2, 1.3 kilograms per cubic meter. And then we're going to have 10 meters per second cubed. And we know that will be watts per square meter. Okay. So what do we have? 1/2, 1.3. Well, we can 1.3 divided by 2 would be 0.65. And then this is 10 cubed, which is 1,000 times 1,000 watts per square meter equals 650 watts per square meter. So that seems like quite a bit of energy, quite a bit of power per square meter, 650 watts. So yeah, it's an important one. But good. So we have that. Now, how powerful is a giant wind turbine with 10 meters per second wind? This is where I want you guys to get some images going. So you can find plenty of images about giant wind turbines, and they will even give their dimensions, and they'll give some average power output. So I'd like you guys to get some images and some information on these wind turbines. So next, wind turbines. We're talking about very large towers, and I can't draw these that well, but they have these enormous propellers, turbines. There you have it. Sometimes these things are as large as the wings of a jumbo jet. They're enormous. Actually, as long as the wings of a jumbo jet, they tend to be narrower. So yeah, how much power can you get? Well, a rough example, the actual fluid mechanics is more complicated, but these numbers will give us very good rough idea of what's going on here. So basically you just have to take the radius here, half the diameter, take the radius r, and use the surface area of a circle, and what we will get is, so let's formulate this as a question first. How powerful is a wind turbine? We have everything up here that we need. So we have power equals the intensity times the area. Remember, intensity is watts per square meter, so if we multiply by area, we're going to have watts. So we've got the intensity, right? So that's this thing here, that was this example here. But since it's sweeping out a circle there, we can just say I times pi radius squared. You have to have the radius. Make sure you don't mix up radius and diameter. Okay? Pi radius squared. And you'll get some rather large numbers. So let's use our number here. So 650 watts per meter squared. And now let's say the radius is, how big is the radius? Let's say 25 meters for starters. So 650 watts times per meter squared, that's I. We've got times pi, and then we've got, say, 25 meters squared. So that's pi r squared. So let's see what we have here. We have 650. This is an approximation anyway, so approximately 650, and then we've got a 3 here, and 25 squared is 625, and that's going to be watts. So I don't have a calculator. What are we going to do with this? We've got 6.5 times 10 squared times 3 times 6.25 times 10 squared. We should be able to come up with something here. So 3 times 6.25, that's 18, so that's about 20. 2 times 10 squared. And then this 6.5 times 2 would be about what we started out with, 13, so 1.3 times 10. 1.3 times 2, so let's do this. So we have, cross that out, 6.5 times 2 would be 13, so 1.3 times 10 to the 1, plus 2, plus 1, plus 2. 2, 4, 5, 6. So we're looking at a million, right? 1.3 times 10 to the 6. You guys can go ahead and multiply this out. We're looking at roughly 1 million watts. Approximately 10 to the 6 equals 1 million watts. So that's how we arrive at the power output for some gigantic turbine like this. We can stop the clock. I have a couple things to say, but I don't want to have this run too long today. Okay, it's not bad. Okay, yeah, so take some time, expand this out in your notes so you have enough room. I just did a little estimate there. You guys can do that with your calculator as well. So for the homework, we want images of these things. And I have in mind some images where they maybe have a little graph that shows different sizes and what the power rating is. So let's just call this homework, and of course it's just added into our notes. Homework, so turbine images, we want different sizes and power output. One thing you might discover if you look for it is wind maps, so maps that show where the most wind is available, say across the United States or across the world. I'll just call that a wind resource map. So see what you can find. You find one of those printed out, it'll be interesting. In fact, you'll see that the wind resource map will show high winds where there are some pretty well-known wind installations, okay? So that's a good one to look for. This especially though, okay? This right here. And I'm going to end with a discussion of our formula, which is very important. Right? I just gave this 10 meter per second example. So once more, the wind power formula, I'll call it. So we have to take a closer look at it, right? We've got that intensity 1/2 rho V cubed. Here's the question: what happens when the wind is going slower? This cubic dependence of the power, you know, power per meter squared. The cubic dependence is very important, and it has the following consequence. And I'm going to write it as a note. Suppose the wind goes down to 1/2 the speed. 1/2 of the original V cubed. Okay, so it goes from what did we have there? 10. It goes from 10 meters per second. That's what we had up there. It goes from 10 meters per second down to 5. Okay, so from 24 to 12 miles per hour, right? So half speed, it still seems like a pretty decent wind. Okay, half the speed, but 1/2 cubed is 1/8. So if the speed decreases to 1/2 of the original speed, the power decreases to 1/8. Okay, so it's a very strong velocity dependence. If the speed doubles, okay, from say 10 meters per second to 20 meters per second, then 2 cubed is 8. V cubed. So now you suddenly have 8 times the power, and things are actually starting to get dangerous. These things can't run in too high of a wind speed. So that's what we call volatility. Very sensitive to changes in the wind speed, because you go to 1/2, you get 1/8 the power. Okay, i.e. 1/8 of the power. Here it's 8 times the power. Okay. So this example tells us that there's a real sensitivity to the wind speed, and it's not just giving you a constant, steady stream of energy the way you might like. Okay. So that's why we actually have to know this formula here, because if we know this, we see why it's sensitive to wind speed. It's not because the wind just dies down completely. It's because even small fluctuations in the wind speed affect the power enormously. So yeah, we could call this volatility. So the output is sensitive to the wind speed. This is why a little bit of mathematical understanding goes a long way. Okay, good. We'll leave it at that. I want you to see some nice images of these different turbines and setups, and if you find a good wind resource map, print that out and put it in as well. Good. See you guys next time.